Bismillahirrahmanirrahim. There are some obvious limitations of the rotating beam test and SE prime that we studied in the last class. SE prime, it is based on a polished specimen specified size. The test standards specify all these things. Completely reversed pure bending load, a specified temperature, usually do it at room temperature, etc. So there are a lot of things to be considered when we calculate SE prime for a certain material. But when it comes to the component that we are going to use in some real world application, it won't necessarily follow any of these, conform to the above. It may have different surface condition. It will have different sizes. It may be subjected to axial loading or torsion or a combination of bending and torsion and what have you. Similarly, it may be employed in an application where the temperature is different from the conditions of the rotating beam test. So obviously there is a limitation of this SE prime. Now we have to figure out somehow SE from the SE prime. Now SE prime either comes from the rotating beam test, or we can also find this out by using half of the ultimate tensile strength of the material. But again, this again is an empirical relationship. So this doesn't give us SE but only SE prime. So how to get SE from SE prime? That is achieved by what we call modification factors. Endurance limit modification factors. And the equation is a simple one. We multiply SE prime with all these factors that take care of the different variations between the real world component and the rotating beam specimen, test specimen. So this is the component to be designed. This is for, rather, from the rotating beam test. Now this equation is a famous one. This is called Marin equation, used extensively for fatigue. Now what about these factors? Ka, this is called surface factor, and we'll discuss each of them in some detail. Kb, size factor. Kc, load factor. Kd, temperature factor. Ke, reliability factor. Kf, miscellaneous factor. Now before we move on and discuss each of these factors, we must recall that, and we have talked about this many times, fatigue is an experimental or an empirical phenomenon. So whatever we are going to discuss and whatever we have discussed to this point, it is based on experiments, not analysis. Sometimes we analyze some things, but the basis for that analysis also is the experiment. So we have to be very careful about this. Whatever we are going to discuss now will have the weight of a lot of experimentation behind it. Let's see what each of these factors mean and what they stand for and how to deal with them. To start with, we start with the surface factor Ka. Instead of a polished surface, our component may have or may be machined. This surface is very different from a polished surface. Cold worked or cast. All these have different surfaces, surface finishes. Hot rolled or forged. Now, when something is polished, it's difficult for the cracks to develop, A, develop, and then B, progress and ultimately cause the fracture. For machine parts or parts of lesser polish, it's easier for the cracks to develop and propagate. So this has to be a factor that reduces the endurance strength of the endurance limit of the material if it is not machined, if it is not polished. So we have this equation and it is given in your textbook. It happens to be equation 6.19. Now the important thing to see here is that these A and B, they are different from the A and B constants that we had used for fatigue strength. Now it's unfortunate that in literature at many places we are using the same symbols, but you must be very careful that this A and B has nothing to do with the A and B of the fatigue strength. Now these A and B can be seen from table 6.2 of your textbook. For each of these conditions you'll have the values A and B and SUT, you know where to find that SUT, and then you can figure out the, so it will be less than 1 because this, when multiplies with this should be less than this one if the surface is anything other than a polished surface. So and similarly for other factors. Now we move on to the size factor. Now this one is the second of our factors. It's called KB. Now this one accounts for the difference between the size of the rotating beam experiment specimen and the actual part to be designed. So why should size be deciding the the endurance limit? What difference does size create in the value of the endurance limit? Uh, the larger the size of the object, the smaller will be the KB, and this we'll see. And the reason being that if you have a bigger specimen, then there is a bigger probability of cracks of all different orientations in it, and out of those cracks, some will have the probability of growing to critical lengths and failing the member. If it's a smaller test specimen, if it's a smaller component, then there is more likelihood that it will have fewer cracks in total and fewer cracks that are capable of reaching the critical crack length and hence breaking the part in two. So it's not something that is certain. It's still something that we talk with some sort of probability. The bigger the specimen size, the lower should be the endurance limit. And maybe you will have some components which are bigger and their endurance limit is higher, but that is statistics. Most of the cases of bigger sizes will have lower endurance limits. So the equation to be used here is, and this is again an experimental based equation. if the diameter, and here we are, for the moment we are talking about circular shaft, circular components. We'll see when we don't have circular components. For the diameter between 2.79 to 51 millimeters, this is our this is the value of our KB. And for other sizes, now if we see this, and this is equation 620 of your textbook. Now there is an interesting case in which this KB can have a value which is greater than 1. And when should that value be? If you have diameter less than 7.62, then because this is a negative sign here, you will get a value of greater than 1. And what is so special about 7.62 millimeters? This is when you talk about the specimen. This is the diameter for the specimen. This is exactly the diameter of the rotating beam specimen. So if any component that you are interested in designing, it is of a lower size than this diameter, then referring to the discussion we just had, it will have less likelihood of cracks extending and then breaking the component. So it should have a higher correction factor than 1. Otherwise, any size, any crack size bigger than 7.6, I'm sorry, any component bigger than 7.62 in diameter will have the value of correction factor KB less than 1. Now this is as far as the circular sections are concerned. Now what if what you are using is not circular to start with? There are plenty of cases in which the section is, for example, square. What if you have this kind of a section, or this kind of a section, for example, or for that matter circular section but it is non-rotating? For example, this kind of a situation where here there's a wall and you are applying a stress, a force here, alternating force, so it's not rotating. So what happens if this cross section is different from circular, or even if the cross section is circular but there's no rotation involved? Because recall that here we are still talking about diameters, so we are assuming here in the size factor that it will be round. So let's talk about this case first. For example, you have this is height is h and this is b, width is b, and for your rotating beam experiment, this is d. Now the practice is that we calculate the area of this rotating beam test specimen that bears more than 95% of the maximum stress. And that because we know that the stress distribution here for bending is something like this. If this is the stress distribution. So this is the area, hashed area. If I say this is 0.95d, then between this and this, the hashed area, this is the area that sees 95% or more of the maximum stress, and that should be, and if we calculate, this is the, let's call it 0.95 stress. and this 0.95 stress for a rotating beam. Let's make this sign here. This turns out to be this. Now, how all these situations are handled is this. We equate this area with the area of all these situations, non-circular members or members which are not rotating, non-rotating members, so that we compare this area, the 95% stress and more stress area, to the area in all these sections which bear 95% or more of the maximum stress. So in this case, let's say this is the, we'll just equate these two and find out what is the equivalent diameter in terms of this that we can use in that equation. So before that, let's first do this. Now D equivalent, if I just write equivalent here, will be a 0.95 stress for any of these sections over 0.0766 square root. Now in this place we'll put the values of the 95%, the areas that take 95% or more of the maximum stress for all these different situations. For just for illustration, I'll do one. This, if this is the one, then this should be 0.95H, because bending, remember, maximum stress is always happening here and here. So the area that takes 95% or more of the stress in this case is, this is B constant, H minus 0.95 H is equal to 0.05 BH. This is your area, which is 0.95, and let's call it rectangular. Now, what should be the equivalent diameter in terms of rotating member, in which all this area takes this 95% load, which represents this thing which doesn't rotate, but still the common thing being that 95% of the stress is taken here. So what should be the equivalent diameter for this case in terms of this? We just put in the value here. So DE turns out to be 0.05 BH over 0.0766 square root, which is around 0.808 BH. So this is the value of DE. So if you have a situation where your cross section is this, not circular, but obviously the size, you know the size, so you want to employ this equation, but this equation, the size factor equation, it only talks about the diameter. It doesn't talk about the B and H at all. So what you do is you calculate the equivalent diameter by putting in these values, and this is the value that you should use here to calculate the size factor. In your book you have different values for these given, and one of the most important ones is this thing, circular section but non-rotating, and this, the equivalent diameter for this one, as you can see from your table, 6.3, along with other different shapes, but this is a very commonly occurring one, so I'll just write it down here, 0.370D. So if component is circular but it is non-rotating, you have to use this diameter for this and then multiply it with this, and then you get the equivalent diameter, and then this one you should use in your equation. So this is how you use the size factor. So circular shafts, rotating circular shafts, this is all you need. But if a shaft is circular but non-rotating, or if it has different shapes, and we have other shapes also, different kinds of sections also, then first find equivalent diameter, then put that value in that equation. Now we come to the load factor. Kc. Now, the manner of the loading in the rotating beam test was bending, pure bending, completely reverse bending stress. Now, in the part to be designed, if it is pure bending, it is also pure bending, then there's no trouble. It's one, because your loading and the loading that was employed to find the SE prime is the same, no problem. Now, if it's axial fatigue, fatigue can be axial also, then you need a correction factor of 0.85. In other words, the endurance limit reduces because of fatigue, axial fatigue, as compared to bending. And why is it so? Let's see. In bending, again, most of the stress, the maximum amount of stress is taken by this area, the cross section. What about the axial? In axial, all this cross section takes equal amount of load, and that's the maximum load. So what happens is that the likelihood of cracks, again we are talking about probabilities, likelihood of potential cracks that grow on to become large and then become critical is larger here than this. So here you are talking about more probability of failure, early probability of failure. Now, this might give an impression that axial fatigue is more dangerous than bending fatigue. In this respect, yes, but overall, no. There's no doubt that endurance limit will be reduced in this case as compared to this one. But there is also no doubt that it is very difficult to produce very high stresses by axial loading as compared to the bending load. Bending is the easiest way to apply loading because of the momentum that is involved. So although by first look you may feel that because it reduces the endurance limit and this doesn't, this is less, this is more dangerous. Actually it is not, but still when we are doing, there can be cases where it can be very dangerous, so we'll be using this correction factor. Now if it's pure torsion fatigue, and there's emphasis here on pure, it's very rarely the case that there's pure torsion anywhere, because there's always some sort of bending involved. But if it's pure, then this is the number that you have to multiply. And what is the basis for this number? We know that in the case of static loading, the shear strength of any material, if we refer to the von Mises theory, it is shear strength of material is about 0.577 of the ultimate tensile strength. Now, there are experiments that have confirmed that even in fatigue, when it comes to fatigue, not static loading, the torsional strength of the material, is more or less the same as compared to the ultimate tensile strength. And this is why, and because we have actually talked about the pure bending where we are talking about the SUTs, so here we are going to use a very similar number. It's slightly bigger, but this is the basis for this. An important point to note here is that these factors are only for pure bending, pure axial, or pure torsion fatigue. If these loadings happen in combination, then there is a completely different approach to be taken, and that will be discussed later in another section. Here we are just talking about individual cases of bending, axial, and pure torsion. Now we come to the next of our factors, the temperature factor Kd. For steels, when we increase the temperature, initially up to about 150 centigrade, there's a slight increase in the tensile strength, and after that there's a drop, and sometimes it's a big drop. Now this ratio is the correction factor. where ST over SRT, this is the tensile strength at the temperature we are talking about, and this is the tensile strength at room temperature. So if we put in the values, and we'll be taking these values ST over SRT. This will be from table 6.4, and we'll be putting, because why is endurance limit, why is this ultimate tensile strength important? Because ultimately we take our SE prime from SUT. So if this, because of temperature, if this uh, ultimate tensile strength is increasing, then so should this. So what we see is, from in table 6.4 up to about 150 degrees centigrade, you'll have a bigger value of ST over SRT than 1. And then after that, after 150, it drops. So our endurance limit should also reflect that. And that is why we use this temperature factor. Now, the next factor in line is the reliability factor KE. Now, this one is very simple. If you recall that we had this sort of a shape, and it was only that we had drawn this line, these lines, at the 50% reliability line when we had found these values of, for example, SE prime and all these values, FSUT. All these values were actually taken when we had drawn this interpolation line at 50% reliability level. So obviously, if our goal is to design something for 50% reliability, we don't need to do anything, because if you look at your table 6.5, you'll see that for a value of 50% reliability, the correction factor is 1. Reliability and KE. There's a table like this. For 50%, you have the reliability, this correction factor 1. You don't need a correction factor basically. But as you increase it to 60% and 99.99%, then this becomes less than, obviously, because what you're talking about now is you are drawing this line here or here, but even if you draw it here, it may be 99.9%, but still there will be some points which are outside it. That is statistics. Nobody can do anything about it. But this depends on your situation. If you need 50% reliability, then this factor becomes 1. Now we come to the final the miscellaneous effect factor. Miscellaneous effects factor KF. Now, any of the things that we haven't discussed, we have discussed temperature, we have discussed size, we have discussed loading, we have discussed reliability, any of the things which we haven't discussed, and there can be many things still. For example, if the environment is prone to corrosion, obviously corrosion plays its part. It will damage the material along with the stress reversal. So corrosion does the same thing. Actually, it destroys the bonds. So if the environment is prone to corrosion, one may be advised to have KF less than 1. Not 1, because 1 is for an environment where there is no corrosion, like your test situation. There are other factors also. For example, if you increase the, for example, residual stresses. Now, residual stresses can increase or decrease the endurance limit. If they are tensile in nature, they'll decrease the endurance limit. So you'll have KF again less than 1 for tensile. If the residual stresses are compressive in nature, then you may have a kf greater than 1. Why? Because compressive stress, residual stress, means that your tensile strength will be increased. Your tensile strength increasing means your endurance limit will increase. So you must have correction factor of more than 1. So residual stresses work both ways. Now, things can be even more complicated than this. For example, in case of case hardening, something like quenching or short peening, in which you either you decrease the temperature drastically so that you have a very hard shell, or you infuse carbon into the surface, or you subject the surface to a blast by very small particles. In either case, you harden the outer shell, and it's let's call it case hardening. So if any of those things is there, then there can be a very tricky situation in which, for example, this is your case and this is your core. This is core and this is case. Now case has been hardened by some sort of compression, and so the endurance limit also increases here. But the core's endurance limit is maybe this, only this one, SE core, and this one is SE case. Now where one needs to be careful is that if this is the center line, this is the center line, you have this here also, then the stress will, and if it is bending stress, for example, then the stress will vary like this. Now you'll be tempted to use the endurance limit for the case, and that's all right because the stress is less than the endurance, no problem, it should have infinite life. But if you see this here, you have this region where the core has a lower SE than the stress that is being subjected to, and if it's a bending fluctuating stress, then this component won't last forever, or what we call infinite life. So these are the things. And so if such a situation is there, first of all we need to make sure that we don't use SE of this case here. But if such a situation is there, then obviously we need to consider using some sort of a correction factor for this situation, so that we are not misled into believing that this case will have an infinite life. And for example, if we apply a correction factor in this case, then this one becomes this becomes this, and we make sure that the stress we are subjecting it is like this, so it will be safe both in case and in core. And there can be many situations where we have a situation where we don't have a factor like the size factor or the temperature factor or reliability factor. We don't have a separate factor for that, and we can just put that consideration over here and adjust our correction factor so that we are not misled into an SE which is not realistic for our situation. So we lump in everything that has not been discussed previously into this factor. There can be many situations, we cannot deal with all of them here, but this is the minimum basis, the basic understanding that you need to have of Marin factors. And in our next class, we'll be applying this knowledge to solving some problems and designing some parts. Thank you.